Hello everyone, my name is Jianshuo Liu, a student in University of Chinese Academy of Sciences, and now I'm presenting my team's recent work, NFCEraser, a security threat of NFC message modification caused by Quartz crystal oscillator. This is a joint work with Professor Haining Wang in Virginia Tech. NFC is a very important technology that enables the devices to exchange messages or perform transactions in a very convenient way. Nowadays, NFC technology has been widely used in our daily application scenarios such as smart tags, digital payments, smart locks, and file sharing. And we can see that the NFC market size has been gradually increasing between 2014 to 2024. Using NFC to exchange messages is very convenient. However, it may at the expense of some extent of security risks. Previous studies have demonstrated two kinds of attacks, naming eavesdrop attack and denial of service attack. For the first kind of attack, the attacker can just place a magnetic field probe at the bottom of MC initiator, such as MC reader, to sense any changes of the amplitude of modulated magnetic signals, and then infer the possible transmission content. For the second one, the attacker can just directly inject the magnetic field signals into the MC communication channels in order to make the MC initiator unable to read any legal content. However, those two kinds of attacks are unable to tamper with specific data transmitted. In this study, we aim to investigate the MC vulnerability in a new perspective. Specifically, we investigate whether the attacker can intentionally modify the received MC message via EMI. We call this vulnerability NFCEraser. We hope that by investigating and reviewing this kind of vulnerability, we can understand the new attack vector against the NFC passive transmission system via EMI, and we hope to inspire product designers to take measures to mitigate new threats and enhance the security of wireless communication devices. The overall NFCEraser attack scheme can be summarized as follows. The attacker can place a magnetic probe under the NFC readers to detect current transmission command content. And when the NFC peer device, such as tags or get gates, are transmitting the response contents backwards to the MC initiator, the attacker immediately injects malicious signals via antenna to the MC circuits, especially to the MC quartz crystal circuits. Then to change the possible amplitude of the magnetic signals sensed by the MC initiator, then manipulates the data content obtained by MC reader. Before successfully launching this kind of attack, the attacker should tackle two key challenges. The first one is signal injection. What kind of signal can be used to tamper with the transmission content in the MC channel? The second one is transmission content control. How to configure the parameters of the tag signal to modify the content of the transmission data payload. Before tackling those two kind of challenges, let's first take a look at the MC passive communication system. The system consists of two parts, namely MC initiator and the device, peer device. The two parts are coupled with magnetic coils with 13.56 MHz modulated magnetic field signal. The carrier signal is generated by quartz crystal oscillator, later in initiator. The overall communication process involves three key stages. The first one is the initiator generates RF field to establish the communication channel. Then the initiator sends reading commands to the MC peer device. When the peer device receives the request content, it will respond via load modulation as described in our research paper. The modulation waveform and the NFC communication frame formats are summarized as follows. NFC consists of two kinds of modes, naming MCA and MCB. Different modes have different modulation waveform representing bits 1 or 0. And for the communication frame, there have two kinds of frames. The NFC initiator should send a data reading or writing command frame to the MC peer device, and the peer device responds with response frame. So let's take a look at the first challenge. There are two options. The intuitive option is to just directly inject magnetic signal into the MC communication channels to overlap the original content, then just modify the possible amplitude of the modulated signals. However, our experiments have demonstrated that stacking magnetic fields onto the channel can cause instability in the energy received by the peer device, so the option A is not feasible. Luckily, we discovered that transmitting specific EM signals to the crystal oscillator will alter the channel carrier's amplitude, thereby affecting transmission data. Let me introduce the detailed mechanism. In general, attacker needs to alter the amplitude of the carrier signal received by the MC initiator to tamper with the bitstream. And the carrier signal is generated by the quartz crystal oscillator circuits. As described before, the circuits consist of quartz crystal with a pair of electrodes and then a pair of capacitors. Then the signal will be amplified by an inverting amplifier, which has a limited and fixed total gain. When the out-of-band frequency signal components and in-band signal components are inputted into the amplifier together, the out-of-band frequency signal will cause the operating point of the amplifier to drift, then results in a decrease in the gain obtained by the in-band signal. The amplifier in NFC quartz crystal oscillator circuits works well under the frequency near the 13.56 megahertz. So any frequency components other than 13.56 megahertz can be considered out-of-band signals. Then we launched the experiments to validate the feasibility of our proposed method. We just inject 230 megahertz sine out-of-band signals to the crystal oscillator's electrodes. Then, since the magnetic field signals outputted from MC coils, then we observed that the signal strength in the frequency domain has decreased around 15%. Then we inject the DSP-C modulated signal with the carrier frequency of 230 megahertz and the base frequency at 6.78 megahertz. We observe that the carrier amplitude increases by 6%, and no extra frequency components are observed in the frequency domain. So this demonstrates that our proposed method is valid. For the second challenge, we proposed two key steps. The first is attacker should detect MC communication model in stage 1 according to the signal modulation depths and waveforms, especially specifically, attackers should sense the modulation waveforms when the MC initiator sends the command frame to the peer device. Then when the peer device starts to respond the response frame, the attacker immediately generates and sends attack signal sequence according to the bit value to be flipped. Then we conduct experiments to validate the overall performance of our proposed attack scheme. We use 6 off-the-shelf commercial NFC communication modules and then aim to flip all bytes of the card numbers in different lengths. And we repeat the task and the attack for 100 times. And the Results suggest that NFCEraser achieves success rates between 63% to 89% under different byte lengths to be flipped. We then evaluate three factors that we believe may have negative impacts on the overall performance. The first one is the attack distance. We place the antenna at a different distance to the NFC initiator's crystal oscillators. Then we found that the higher attack distance, the higher energy of attack signal required. The second one is probing distance. We place the magnetic field probe at different distances to the MC coil. Then we found that with the probing distance increases, the overall sensed magnetic field amplitude variance decreases accordingly. And at the probing distance more than 4 centimeters, it is almost impossible to detect amplitude changes. The third one is noise power. We place the NFC communication module in a white noise environment with an average distribution of 1 to 500 megahertz and 6 different noise power. We observe that when the EMC power is around 40 watts, the success rate of the attack is less than 50%. That's all. Thanks for listening.